And so the difference between the chapter 2 and chapter 3 is that in chapter 2, we developed all these concepts from a very mathematical point of view, right? And we introduced a random variable, and then we said we're going to work with probabilities, with a survival function, with a CDF, with the expected value, but all in a very purely mathematical way. So what we now want to do in chapter 3 is, what if you actually need data to say something about this life expectancy or to calculate a certain survival probability? So where are you going to find this data, and how are you actually going to work with these numbers? So I can imagine that this is a very necessary chapter for you, to step from the purely mathematical side from chapter 2 to an actual more practical setting in this chapter. So first thing to note is, what is a life table? So a life table, also called a mortality table, if you're a little bit more pessimistic, well, that is a sort of tabular way. So it's a table, it's a tabular format of getting access to these survival and mortality probabilities. So I show you the example that we use in the second chapter of the data chem course. The second chapter, you will work with that next week. This is a life table for Belgium, and I downloaded the data for some reason from the year 2013, right? So this is mortality data, lifetime data for one particular year. And what we see here is that we list here integer ages. So we go from 0 to 10 or from 0 to 9 in this case. Why? Because I'm only printing the first 10 lines from this life table. So if you look at a particular year, you'll find in the life table for every age, going from 0 to 100 or 120 or something, you'll find information, for example, about the QX. For example, about the future life expectancy, the EX. And also about other quantities, here denoted with LX and DX, but I still need to introduce or explain what these quantities are, right? So for now, what is a life table? It's a table in which you can find information about this QX, this EX, etc. What is apparent here is that you'll only find information in the life table for integer ages. Why? Because it's, of course, way too much detail. It would lead you too far. It's impossible to print something in the table for every continuous age that you can imagine. So one of the things we'll need to do is figure out a way to go from this integer ages to the continuous settings that we discussed in the previous chapter. Okay. One last thing to mention here, this table is taken from the Human Mortality Database. So that's a source where you can find a lot of statistics for different countries on mortality, survival, life expectancy. It's maintained by Berkeley and by the Max Planck Institute. So it's a very rich and powerful source of information if you want to know something about demographic statistics. Good. Questions? So here are the goals for this chapter. We want to be able to work with a lifetime, with a life table, sorry, that shows us mortality rates at integers only, right? Be careful, what do I mean with the mortality rate? That's another way to refer to the Q-axis. So mortality rate, that's QX. That's the same for actuaries. What else do we want to do in this chapter? We want to develop a fractional age assumption. That's the assumption that will allow us to go from the discrete ages in the table to the continuous settings that we developed in chapter 2. For example, if you need to evaluate Sx in t, where t is a real number, positive real number, right? Then you need to be able to go from these integer age data, which are in your table, to a continuous time setting. So we're going to explain how to do that in this chapter. And then finally, we're going to say something about how these mortality data, how they change over ages and over time. And we'll also say a few words about what is the difference between demographic data, mortality data, at the level of the national population, for example, in China or in the Netherlands or in Belgium, compared to when you look at statistics for an insured population. So a group of people that bought a certain product from an insurance company. What could be the difference there, and what could we say about that? So let's say that you have access to a certain survival model expressed as TPX, where T is in continuous time, and you would need to construct a life table from this survival model, right? So in this case, I frame it as follows. I have a survival model, look at chapter 2, and I want to sort of summarize this survival model into a life table. How can I do that? Well, then I have to decide, first of all, from which age on until which maximum age I want to put data in my life table. And we often call this starting age, x0, we call that the radix, and we call, or we denote the maximum age in the table, we denote that often with omega, but that's purely a choice, that's or a convention. Yeah. So what can I do? Well, in the life table, I'm going to list this LX. You may remember that from my first sheet. I'm going to define this LX as a function of x that I can construct as follows. I'm going to start with LX0, and that's going to express the group of people that I have, the size of the group of people that I have at age x0. And I'm going to multiply this LX0 with the survival probability of somebody who's x0 year old, survival probability evaluated over t years. And that's going to give me the LX0 plus t, right? So I'm doing something quite complicated at this point. I'll start from a given expression for the TPX. I start from an initial group of people expressed as LX0, and then I say, well, then I can come up with the size of the group of people alive at age x0 plus t, that's this guy, by manipulating these concepts, by multiplying these two. If you would start from there, then you can further gain a bit of insights into what these, or how you would structure these LX plus T's. And you can do that as follows. So if I would be interested then in capturing what is then the LX plus T, if I only have access to this function, well, then I should rewrite the x plus t as x naught plus something, right? And that can be done in the following way. So that would be x naught plus x plus t minus x naught. That's exactly the same here, left and right hand side. But if I write it like this, then I can say, well, then the Lx plus t, using my function definition over here, that's Lx naught times, and then a survival probability. Survival probability for an x0 year old who has to survive another x plus t minus x0 years. And using the multiplication rule, I can split the survival probability in the following two probabilities multiplied. I can say I start with an x0 year old. He has to live for another x minus x0 years. He reaches then hx and needs to survive another t years. So if I work that out, I'll see that I then find the following intuitive expression. Lx plus t is Lx multiplied with tpx. And that's eventually what I want to come to. So if I have a survival function, the tpx, then I can bring up this column, the Lx column in my life table by using the following connection. Yeah. And this all sounds a little bit weird, but we can connect this to the expected value of a binomial random variable. And that's what I'm going to do on the next step. So this is an important connection. It's the connection between the L quantity, the L column, the L variable in my life table, and the survival function, the TPX. Yeah, and the connection is as we build it up over here. Now, myself, I find this a bit of a complicated way of looking at this, looking at these guys. So let me first give you a more intuitive interpretation, and then I'll answer Sally's question. So more intuitively, we could say, well, these LTs, that I see in my lifetime table. They are the expected values, if you want, of an underlying random variable denoted here with capital LT, which is a binomial random variable that expresses the number of survivors until hx plus t from a group of Lx independent lives that I start with at hx. Because if you look at a binomial experiment, then you start from a group, you're running independent Bernoulli experiments with a certain probability of success. And here the probability of success is the TPX, the probability of surviving until hx plus t. So if you use then your knowledge from a binomial distribution, then you know that the expected value of a binomial random variable is the number of experiments you're running multiplied with the probability of success. And that's how you can see these Lx's in the lifetime table. Lx plus t is the expected number of survivors up to hx plus t from an initial group of people with hx, where the probability of surviving is tpx. So what we have here, what Sally is referring to is we want to know x plus t minus x0 px0, right? So we start at h x0 and we want to know what is the probability that you will survive until h, and then you have to be careful, so that's h x0, that's where you start from, and then the duration that we consider is what is on the left in the subscript, right? Because we noted this is the starting age, and in this actuarial symbol on the left, you always have the duration over which you want to calculate the survival probability, right? So if you would look at our symbol TPX, then the X is always the age you start with, and then the T refers to the length of the interval that you're considering, right? So here we are looking at what is the probability that you will survive until x0 plus x plus t minus x0. So that is, if I cancel out the x0s, until hx plus t. So it's a bit of a, say, a bit of a strange way perhaps of writing it. I agree with that, but that's because in our lifetime table, we would start, as Stijmen indicated, from a certain age x0 on, and we would go there until, yeah, let's say hx plus t, and then finally omega. Yeah, it's to make the connection with the x0 age, that is our starting age in the lifetime table. And now what we do here is we use the multiplication rule. So that means that I can say, well, you first have to survive until a certain age, and then I multiply with the probability of surviving for the next considered time point, time interval. So what I'm going to do here is I'm going to break up this survival probability by saying it's like this. You first have to survive a duration of x minus x0, and then when you reached hx, I want you to survive another t years, right? Because that's essentially the same, because we're looking here at what x, that's what I wanted to say. And then you go until hx plus t, right? So the step in between is hx. The length of this interval here is then, this length of this interval is x minus x0. And the length of the interval here is t. That's where it's coming from, yeah? So the first probability here captures the first part over here, and the TPX is then capturing the probability that as an x-year-old you will survive until age x plus t. And if we look at the initial expression, we want to know what is the probability that for an x0-year-old, he or she will survive another x plus t minus x0 years, right? So if I look at the red guys, it's in total x minus x0 plus t, or put differently, it is x plus t minus x0. That's the length of the interval that I'm considering.